Okay, this is the first in a series of videos introducing the second law of thermodynamics. This is chapter 5 in your textbook. So, first of all, we're going to be very soon talking about cycles. A cycle is just a series of simple processes, like the sort of thing we've been doing, but I'm going to go through enough different processes that the initial state will eventually get back around to being what is the final state. Now, if power is produced going through this cycle, it is called a heat engine. And if power is required, it's going to be called a refrigerator. Now, we may use it for different purposes, but that's going to be just our general broad classification, which will make solving problems a lot easier if I can categorize everything as either a heat engine or a refrigerator. Now, this is a very simple concept of a heat engine. So this is just a 4-step power plant. It's actually very similar to how actual power plants work. As I go through this, in this particular case, I go through a boiler, then I go through a turbine, then a condenser and a pump, and eventually I get back around to being the same initial state. Now, because it is a cycle, I know that the net work equals the net heat transfer. Okay, that was one of our first law results that we haven't really used, but it was an important and significant one. Okay. If it's a heat engine, it produces power, so the net work is positive, meaning the net heat transfer is also positive. But the net work, well, it's going to be produced in the turbine and required for the pump, and so I want the amount produced more than the amount required, so the value of the work of the turbine is going to be greater than the value of the work of the pump. So, kind of a summary here, my net work is going to be positive, so my net heat transfer is positive. The work produced is greater than the work required by the pump, but it's also going to require a net heat input because I'm going to produce power. So these things are all going to be really significant and important things that define a heat engine. So what about in a refrigerator? In a refrigerator, we are going to have net work is negative. They are going to require power because they're going to bring heat or take heat out of the system. So Q net is going to be negative. So these are always going to require power, but they're also going to remove more heat than they produce. This is the way a simple refrigerator works. So it's going to come and it's going to go through a compressor, bringing things to high pressure, go through a condenser, which takes heat out of this little net system here, an expansion valve, and an evaporator. Now, these are all the sorts of devices that we learned how to analyze in the previous chapter. So there's nothing surprising about this, but I'm going to require work in the compressor. Expansion valves do no work or heat transfer, and then I'm going to take heat into the system in the evaporator and send it out in the condenser, but the net heat transfer is going to be out. If I want to talk about how these things perform, I'm going to want to use some sort of a ratio. The easiest way, engineers like numbers. They want to say, not that, oh, this is a really good refrigerator. They want to say how good it is. So you want a number that relates this. And so kind of an overall way that we describe how good something is, we look at a ratio of whatever it is I'm trying to get out of it, so the desired effect of the process or cycle or whatever, divided by whatever the cost of running this cycle is or running this process. So this is sort of a generic definition. Now, if I'm talking about a heat engine, then we're going to name it thermal efficiency, and my desired effect is power, right? When you talk about your car, your desired effect is how much power can I get? And the cost of operating it is going to be the amount of fuel or energy input I'm putting in. So the net work over the heat transfer in, which we're going to designate as QH. this will be my thermal efficiency. Now this is going to be a positive quantity. This is going to be a positive quantity. So I'm going to get a positive answer here. W net is equal to Q net, right? So that was the net work for our entire cycle equals the net heat transfer. Q net over QH then is the same as W net over QH. But Q net is the heat transfer that happened at that high temperature, okay, which was my boiler, and QL is going to be my heat loss from the system in the condenser. Okay, so the sum of QH and QL is going to be my Q net. Well, QH over QH is 1, QL over QH, well, I get stuck with that. I end up with this expression here. Now, most of the time, I mean, this is absolutely correct, but we want to talk about things as values. So if you want to talk about the value, well, QL is actually negative and QH is positive. So this is going to be a quantity that's less than 1. So I'm going to take 1 plus something negative. Okay. If I use absolute values, I can see a little bit more clearly here. I'm taking 1 minus something positive, which means that I've got an upper limit here of 1. Okay. And that's going to be really important for us later. Now, what about those refrigerators? Now, if I have a refrigerator, my goal is to cool things. The concept is the food in the refrigerator is the cold item, so it's the heat transfer happening at low temperature. And then if you stand behind a refrigerator, you can feel that it's warmer back there, and it's certainly warmer than my food. And so I'm going to have heat out into the hot temperature, the room. So my goal is cooling the cold temperature. But the cost is I plug it into the wall and I pay for power, which is primarily running the compressor. So QL over W net. Now, this is going to be heat into my system and out, and work into my system. So this is going to be positive and negative. We really would rather think of these as absolute values. So take an absolute value. I end up with this as my definition. My goal is heat transfer out of the cold stuff, the low temperature. The cost is power, my net work. But W net is Q net. And using an argument I had similarly, I can do some algebra. This is QH plus QL, taking absolute values of these. The QH is going to be, well, let's come back to our picture back here. Okay, so this is going to be my hot, my cold, and I'm going to have my signs when I work them out here. But sometimes I don't want to use my refrigerator to get cooling the cold stuff. Sometimes the goal is I'm going to use the refrigerator as a heat pump. A heat pump is, well, air conditioner is a sample of a refrigerator. A heat pump is very similar to using an air conditioner, but my goal is to heat up my house. So it's a form of a heater that really is just taking the hot part, the hot exhaust off of my air conditioner, essentially. It's like huddling back behind your refrigerator trying to warm up on a cold day. And so my goal now is the heat transfer at the high temperature. So it's coming off of the heat pump or the refrigerator, and then I've got my network here. When I play the algebra game, I end up with this expression. Now I'm going to pause the video here. We're going to stop and start again and take this analysis a little bit further and talk about possibilities.